In this video, I would like to talk about the theory of boundary value problems. In particular, we're going to discuss the existence and uniqueness of solutions to boundary value problems. The focus here in this video will be on linear second-order boundary value problems, and the differential equation for such boundary value problems has the following form. We have the unknown function u, which depends on the variable x, and the differential equation is u prime prime of x plus p of x times u prime of x plus q of x times u of x equal fx. So we've got the second derivative of u prime prime. Then we've got a term associated with the first derivative, px times u prime of x. Then we've got a term associated with the function itself, q of x, u of x. And we have got an inhomogeneous right-hand side, f of x. Now that boundary value problem is posed over some interval from a to b, and at the endpoints of that interval we impose boundary conditions. In fact, there's many different types of boundary conditions we could impose. I'm only writing down the most important ones here. Namely, on the one hand, we've got Dirichlet boundary conditions that we can impose. For example, we might say that u at a equals some number ga, and u of b equals some number gb. Those are called Dirichlet boundary conditions. With Dirichlet boundary conditions, we fix the function values themselves along the endpoints of the interval. There's another type of boundary conditions, the so-called Neumann boundary conditions. U prime of a equal ha, and u prime of b equal hb. So with Neumann boundary conditions, we fix the first derivative of the function. There are also other boundary conditions, such as roping boundary conditions, for example, but we are not going to discuss them here. So as you can tell, if you come up with some interesting type of boundary conditions, you can get those boundary conditions named after you. Now, from the theoretical point of view, it is interesting whether for different type of boundary conditions, we have got the existence of a solution, whether the solution is unique. However, for boundary value problems, that is considerably more complicated than for initial value problems. That corroborates a mathematical intuition that I already mentioned in some previous videos. Namely, even though boundary value problems involve differential equations just like initial value problems, the mathematical look and feel, so to speak, is completely different. In the case of initial value problems, under fairly mild conditions, we can already guarantee the existence and uniqueness of a unique solution. A simple example shows that this is not true for boundary value problems. So we're going to have a look at a boundary value problem which looks fairly innocent but does not have a solution. We consider the differential equation u prime prime of x plus pi square u of x equals 0, where x is in between 0 and 1. That is a second-order differential equation, and we impose the boundary conditions u at 0 equals 0 and u at 1 equal 1. Now, with the theory of differential equations, one can show that the general solution to that differential equation has the following form, namely u of x equal c1 times sine of pi of x plus c2 times cosine of pi of x. So you might say u of x is a superposition of a scaled sine function and a scaled cosine function. Okay, now let's try to find the constants c1 and c2. We recall two facts, namely on the one hand, sine of 0 is the same as sine of pi, namely equals 0. And we have that cosine of 0 equal 1 and cosine of pi equal -1. And so we see that on the one hand, the sine function has no contribution to the boundary values. C1 is not determined by the boundary values. But we see that C2 must be 0. Namely, if u at x equals 0 equals 0, then C2 must be 0. There must be no contribution by the cosine function. But that means that u of x is basically just a scaled sine function. And that scaled sine function, sine of pi times x, scaled with some constant C1, can never satisfy u of 1 equal 1. Consequently, no solution exists. And consequently, this boundary value problem does not have any solution. Another example shows that even if a boundary value problem has a solution, that solution is not necessarily unique. Again, we have a boundary value problem that looks very innocent. U prime of x plus pi square u of x equals 0, where x is in between 0 and 1. And this time we have the two boundary values u at 0 equal u at 1 equal g, where g is simply some real number. One can show that all the solutions to that boundary value problem have the form u of x equal c1 times sine pi x plus g times cosine pi x, where c1 is just some arbitrary constant here. Well, all functions u of that form satisfy the differential equation, and they also satisfy the boundary values. The boundary values are completely determined by the cosine part of the solution, and the sine part of the solution has absolutely no influence on the boundary values. So we see that indeed there are infinitely many solutions to that boundary value problem. Now we take a look at another example of a boundary value problem. In the next example of a boundary value problem, the solution properties are even more intricate. This time the differential equation depends on a parameter lambda. So let's suppose that u prime of x we assume that parameter lambda is non-negative. The differential equation is u prime of x plus pi square times lambda square times u of x equals 0. Where again x is in between 0 and 1. The boundary values are very simple, namely u0 equal u1 equals 0. So we've got homogeneous boundary values. Let's recall the general solution to that differential equation. U of x equal c1 times sine of pi times lambda x plus c2 times cosine pi times lambda x. The general solution is very similar to the general solution of the previous two examples, except this time we've got this parameter lambda within the function. Again, we would like to determine the coefficients c1 and c2. Now, on the one hand, plugging in x equals 0 fairly easily shows that c2 must be 0. So the cosine part must be 0 in fact. And so u of x equal c1 times sine pi lambda x. Okay, what can we tell about c1? It turns out that the boundary condition at x equal 1 can tell us something about c1 and lambda. If c1 of sine pi lambda is equal to 0, which means u of 1 equals 0, then the boundary value u1 equals 0 implies, first and foremost, that C1 times sine of pi lambda must equal 0. Consequently, well, this is true if and only if C1 equals 0 or the sine part, sine pi lambda, is equal to 0. And the latter is only the case if lambda is a non-negative integer. That's just due to the fact that the sine function assumes the value 0 only at multiples of pi. And that leads now to the following interesting observation. If lambda is not a negative integer, then this boundary value problem only has a trivial solution, u of x equals 0. But if lambda is a non-negative integer, lambda equals 0, 1, 2, 3, and so on, then in fact the solution space to the differential equation is one-dimensional. It's the span of sine pi lambda x. So then we have got an infinite number of solutions that look like C1 sine pi lambda x. In fact, the setting here relates to the theory of eigenvalues and eigenvectors that we already know from linear algebra, except this time we're not talking about matrices and vectors, but about differential operators and functions. So conceptually, the solution U to that boundary value problem, if it is non-trivial, is an eigenfunction to the eigenvalue lambda of something that we call a differential operator. The differential operator maps the function u to the negative second derivative of the function u, and the differential operator is only considered over the functions with Dirichlet boundary conditions. That is only a rough outline of the theoretical background for this example. Of course, there's a huge body of theory about eigenfunctions to differential operators. In fact, what they might not have told you in linear algebra is that the theory of eigenvalues and eigenvectors for matrices is in some sense only a preliminary to the theory of eigenfunctions and eigenvalues in advanced analysis. In some sense, eigenfunctions are the raison d'etre for everything in the theory of eigenvalues and eigenvectors. Such eigenfunctions and eigenvalues are particularly relevant when you go into the areas of quantum mechanics, for example. We will also take a look at a discrete analog of that when we discuss numerical methods for boundary value problems. So at this point, we can already give some piece of insight on the nature of boundary value problems, in particular in comparison to initial value problems. In some sense, evolution problems are local. Namely, if we know the state ut of some function ut at some point in time t, then we already know us, at least for some times s that are close to t. And as we know, for example, under some very mild conditions on the differential equation, we can show the existence and uniqueness of the solution, at least locally. By contrast, we may conceptualize boundary value problems as non-local. Namely, every value ux at any point x influences also the function u everywhere else. For example, if you change the coefficients of the differential equation at some corner of the interval, then the effects will also propagate to every other point of the interval. There's also a physical interpretation to that. Namely, fairly often, boundary value problems describe the limit, so to speak, of an evolution problem. For example, if I take the heat evolution and let the heat distribute itself over time, then at some point I'm going to approach a stationary heat distribution. And as we've seen in the last video, that stationary distribution can be described by a boundary value problem without any time variables. Conceptually, as we take the limit for t going to infinity and approach this stationary distribution, every point in space has a time to interact with every other point in space. Every information at any point in space has a time to propagate to every other part of the space interval. And this non-locality of boundary value problems is perhaps one reason why the solution theory to boundary value problems is so much more complicated than for initial value problems. Okay, after all these theoretical considerations, let's move on to something more practical, namely the numerical solution of boundary value problems. So suppose we have got our model boundary value problem with the differential equation u prime prime of x plus p of x u prime of x plus q of x u of x equal f of x with some boundary conditions. Let's suppose we pose this over some interval from a to b. The solution theory for such boundary value problems is fairly complicated, and this considers the existence of solutions, the uniqueness of solutions, and also then the construction of solutions can be fairly complicated. In the case of linear differential equations, there already exists quite some literature, but already in the case of differential equations with constant coefficients, you have to do quite some case distinctions. Furthermore, generally you will encounter, and furthermore you will have to deal with imaginary numbers, which is not necessarily taught in linear algebra classes. And if you have differential equations with non-constant coefficients, then pretty much all bets are off and you have to read quite some literature. But how could we construct a solution to that boundary value problem? Well, one possible approach actually uses theory for initial value problems. So we have the same differential equation, but let's suppose we consider the Cauchy problem associated with that differential equation. And some arbitrary initial conditions at the left endpoint of the interval. Since it is a second order differential equation, we pick an initial condition for the function u itself and also for its first derivative. So u of a equals c1 and u prime of a equals c2, where c1 and c2 are just some arbitrary constants. Okay, what we can do is we solve the initial value problem with those generic constants c1 and c2, and then we try to fix c1 and c2 such that the boundary conditions of the initial problem are satisfied. This is not necessarily constructive, and most importantly, this technique is only restricted to one-dimensional boundary value problems. Nevertheless, that approach has also sparked some interest in numerical analysis and has led to the development of a class of numerical methods that is known as shooting methods. So the basic idea of shooting methods is that you fix C1 and C2, then you apply one of the many time-stepping solvers to find a solution to that arbitrary initial value problem. You could use explicit Euler, you could use Runge-Kutta, multi-step methods, whatever. And in that manner, you go from the left endpoint of the interval to the right endpoint of the interval, and then you try to modify artificial initial conditions to hit the desired boundary condition at the right endpoint of the interval. Well, those techniques are fairly old, and the most important constraint of these techniques is that they only work for one-dimensional boundary value problems. You cannot use them for two-dimensional or three-dimensional boundary value problems. So in particular, I've never met anybody in numerical analysis who's actually doing active research on shooting methods anymore. The majority of research for numerical methods on boundary value problems is either on finite difference methods or on finite element methods. Both of those techniques are fairly common in computational physics and engineering. And for that reason, our discussion on numerical analysis is going to focus on finite difference and finite element methods. We will only deal with a one-dimensional case, but I think this will give you some valuable insight in how this is done also. I think this will give you some valuable insight in how these methods work, and that will also help you to generalize them to high-dimensional problems, depending on what type of mathematics you specialize in your future.